Hi, this is Gabriel. Welcome to the fourth part of the Robot Components Beginner series. In this video, we'll explore how to visualize different robot poses in Rhino by making use of the forward and inverse kinematics components of RC. I will start off with the IRB 1205 preset component again that we also used in the last part of this course. By default, any robot component will be visualized in the Rhino viewport with all axis values set to 0 degrees in rotation. However, by using the forward kinematics component, we can see the robot also in different poses. We can find it under the simulation category of robot components. As you can see, it comes with 3 inputs. The first input will take in the robot of our choice. In this case, I'll plug the IRB 1205 robot into it. Let us turn off the preview of the robot definition component. As you have noticed, we can still see the robot. This is because the forward kinematics component comes with its own preview, so we can see any changes in the axis values. Let's move on with the second input. This one takes in a robot joint position parameter, which contains the rotation values for each axis. We can create custom robot joint positions by using the robot joint position component that is found in the code generation category. Let's place it on our canvas and connect it to the robot joint position input of the forward kinematics component. The robot joint position component comes with one input for each robot axis. Let us quickly create one numeric slider for each input that goes from -360 to 360 degrees. By moving each slider, we can now simply change the rotational value of each axis and explore different robot poses. Notice that the visualization turns red as soon as we break one of the defined axis limits of the robot. This way, we always know if the robot is able to reach the desired pose or not. Before we continue, I'll quickly reset all sliders to a value of 0. The third input of the forward kinematics components handles the external joint position which are needed when working with an external axis. A custom external joint position can be created by using the external joint position component from the code generation category. However, since our robot definition does not contain any external axis configurations, we'll ignore this input for now and move on with the outputs of the forward kinematics component. The first one will give us a list with all the different mesh parts of the robot. The second output contains the end plane of our robot. This is the plane the robot actually reaches by using the defined joint position. The third input will give us a list of all the external axis planes. Since we are not using any external axis, this list is empty in our current example. Even though it is nice to pose our robot based on a joint position, most of the time we don't really know the axis values for a desired pose. For example, when we want to reach a specific position in space. In this case, we want the robot to automatically figure out the correct joint position for a desired target. That's when we need the inverse kinematics component. Let us turn off the forward kinematics preview for now and grab the inverse kinematics component from the simulation tab. Like the forward kinematics component, it also comes with an input for a robot parameter where we can directly plug the IRB 1205 in. The second input takes in a movement parameter which needs to be created first. Let us create a basic XY plane and connect it to a point. This plane will be the target plane for our robot. Let us grab the robot target component from the code generation category. The robot target component comes with 3 inputs. A name input that is based on a text parameter, a plane input that defines the actual target plane, and an axis configuration parameter. We'll get to that last one a little bit later in this video. For now, let us plug our XY plane into the plane parameter input and the rob target output into the movement input of the inverse kinematics. You might be wondering at this point why we can plug a target parameter into a movement input. This is because in this case robot components will automatically convert the target to an absolute joint movement to make it usable with the IK. We'll talk about different movement types later in this course. As you can see, the IK immediately created a new preview of the robot pose for us. However, right now our target is directly located under the robot. I'll move the position of the point parameter to a location that makes more sense. The IK will continuously update the robot preview in this process. As you might have noticed, even though we relocated the target plane to a better position, there still seems to be something wrong. That's because our target plane is facing the wrong direction. We can use the plane visualizer of robot components to see this in more detail. As you can see, the Z-axis of the plane indicated by the blue color is facing upwards, so the robot tries to approach it from the bottom. We can easily fix this with one of the flip plane components provided by robot components. Like the plane visualizer, we can find them in the utility section. I will use the flip plane Y component, which simply inverts the X and Z axis of the plane. Let's plug our plane into it and connect it to the plane visualizer and the plane input of the robot target. As you can see, the facing direction of the plane got inverted. We can also use the flip plane X component to achieve a similar effect. However, this component will flip the Y-axis instead of the X-axis to invert the plane. Now that we have fixed the facing direction of the plane, the robot is approaching the target from the top. Let's move the plane around. I'll also quickly rearrange the canvas. Oftentimes, there's not just one solution for reaching a desired target plane, but there might be multiple valid joint positions. That's when the axis configuration of our robot target gets more interesting. I'll plug a numeric slider into it. Usually, it should have a range between 0 and 7. If we now change the value of the slider, you'll see that the robot will find multiple solutions for reaching the target plane based on the axis configuration. However, most of the time you'll find that not all of them are valid. As usual, this is indicated by the preview turning into a red color. That's it for now, and I hope to see you in the next video where we'll explore different types of movement.